Hey, it's me again. So now what I'm going to look at is the Stork Enamine reaction. So we looked at the Michael reaction, and before that we looked at some collation reactions. So we're going to go ahead and look at what's known as the Stork Enamine reaction, which actually involves conjugate addition. And so the Stork Enamine reaction involves 3 steps. And so I'm going to go over the 3 steps, but what you really need to know is like the overall reaction. And so we'll look at the overall reaction at the very end. So the first step is the enamine formation from a ketone. And so we've seen this reaction before when we went over the aldehydes ketones chapter. And so remember I said we think about the loss of the water. You have nitrogen in your ketone there, so I'm losing water. So the nitrogen touches on where the carbon is. Usually form your imine because you lose H2O, but when there's only one hydrogen here to lose, it takes the other hydrogen from the adjacent position, so you end up forming your enamine from that. Okay. The next step is a Michael type addition to an alpha beta unsaturated carbonyl compound. Okay, so I'm just trying to draw this. Let's go ahead and I'll just move it down so you can see a little better. And so it's a Michael type addition, so it adds to the beta position here, or you could put the negative charge going up on that. Either way. I'll go ahead and show it with the minus charge in that carbon, even though it can be stabilized to resonance with that carbonyl. And so what you end up seeing here then is that being protonated, taking off the carbon. Let's go like this. You see a proton transfer. So you'd have that compound. So you've got added to that alpha position to your carbonyl you started off with, and you underwent a Michael reaction. Then you have enamine hydrolysis back to your ketone. So you hydrolyze this part now. Let's go ahead and draw that. So I just drew this again. And I hydrolyze that and get my carbonyl back. So overall, if I'm looking at what exactly happens here, to start out with my starting material all the way to the product, I'm just seeing it undergo a Michael addition. So what makes this different than the normal Michael reaction, the normal Michael reactions, we have a dicarbonyl compound. And so we use a base, remove the alpha proton in between the two carbonyls. That adds to the beta position of my alpha beta unsaturated carbonyl compound. So basically what the Stork enamine reaction is just a way to do this, a Michael addition with a monocarbonyl compound. Okay, and you use that using your peroxidine here. So the peroxidine reacts, it undergoes a Michael reaction, so you end up with peroxidine back at the end as well. So that just serves as a catalyst. So a catalyst is something that speeds a reaction or allows the reaction to take place, but is regenerated in the end or is not used up in the end. So you do get it back in the end. So it's just a catalyst for the reaction. So if I was drawing the overall reaction for this, and that's the part that I want you to know. As you see a monocarbonyl compound, you have some kind of an alpha beta unsaturated carbonyl compound. You're given that peroxidine as your catalyst, and so your overall reaction will just be your carbonyl compound, your monocarbonyl compound, with attached the beta position to the alpha position of that monocarbonyl compound. So that is the overall reaction. So let's look at some examples. This one says, how might you use a Stork enamine reaction to prepare the following compound? And so I'm going to look and see, okay, where can I take this apart at? Well, if I look at this part, so there is an alpha position to this carbonyl, and if that's an alpha position to that carbonyl, here's a beta, here's that second carbonyl alpha beta. So here's the adjacent position to this carbonyl, attaches this beta carbon of my second carbonyl. So that's the part where I'm going to take it apart at. Monocarbonyl compound. Okay, so there's one compound, there's my alpha position for this one. I'm going to draw this one. So here's my CH3 double bond O. Here's my alpha, here's my beta, then a CH3. So here's my alpha, beta, CH3. So my double bond goes between the alpha and beta positions. And so that would be the two reagents I would need. And then I would have the peroxidine as my catalyst to show that is a true Michael reaction. So let's go ahead and look at some problems in your textbook. So this is what process you result after hydrolysis from reaction of the enamine prepared from cyclopentanone and peroxidine with the following alpha beta unsaturated acceptors. So cyclopentanone plus this compound, I'll just put my plus here, plus peroxidine. Okay. So here's my monocarbonyl compound, my ketone. So So here's an ester, so here's my alpha, my beta. So the alpha position of my carbonyl compound is going to attach to the beta position here, so Michael addition. So CH2, CH2, CO2 ET. Okay. Let's work C. So again, cyclopentanone plus pyrrolidine. Okay. So alpha position to my monocarbonyl compound is attached to the beta position here, so that's CH. Here's my alpha, here's my beta. So attached to that beta, I have a CH3. And just finish the molecule from there. So I have my CH3 attached to my beta position. Then this becomes a CH2, and I have C double bond O, CH3. So that's the Stork Enamine reaction. -20 is going the opposite direction. You're given the product, and you have to show what you started with. Same concept though. So here, if I look at, so I have a carbonyl compound that I could use. Now here's a beta, alpha, and then a nitrile, so that also works for my Michael receptors. So when I take it apart between that beta and the alpha, I just put a double bond. Same thing here. In this case, I have a 6-membered ring. So I'm attached to the alpha position, and I do have 2 carbons and another carbonyl, so that'd be your Michael receptor. I use the pyrrolidine. So 6-membered ring. Now there would be a CH2, CH, C double bond O, O, CH3. So just continued my structure from there. So that is the Stork Enamine reaction. And so the next one we're going to look at will be the Robinson annulation reaction. And it's one of the more difficult reactions that we'll cover this semester. It combines a Michael reaction with an intermolecular aldol reaction, but we'll look at that one in the next video. See you there.